ghostly Whistler waves created by lightning, may help to protect experimental nuclear fusion reactors, and make limitless energy a reality. That's the claim made by a group of researchers, who detected the ghostly presence of the waves inside their reactor, in what they say is a world first. Whistlers are normally found whipping across the ionospheric layer of the Earth's atmosphere, at heights of up to 620 miles above the planet. Now, scientists say they have detected the mysterious electromagnetic waves inside their reactor. They were surprised to find that whistlers appeared to help prevent runaway electrons, produced in the nuclear fusion process. These particles, traveling at ever faster speeds, risk burning holes in the equipment if they accelerate too fast. Experts hope to tame this by developing methods of controls based on their findings, which could lead to a breakthrough in fusion reaction. The findings were made by a research team led by the U.S. Department of Energy's DOE, Oak Ridge National Laboratory, ORNL. For decades, experts have been building the scientific basis for nuclear fusion as an energy source to generate limitless electricity. Fusion happens when the nuclei of lighter atoms join under extraordinarily high temperatures, to create a heavier nucleus, releasing energy. The hot, fused atoms form a plasma that is confined by high magnetic fields in an experimental vessel called a tokamak, designed to withstand conditions hotter than the sun. Strong magnetic fields are used to keep the plasma away from the reactor's walls, so that it doesn't cool down and lose its energy potential. Instabilities can occur in such an extreme environment, causing a dramatic quenching, or cool down, of the plasma and producing runaway electrons that could veer off and burn holes in the tokamak's interior wall. Using sophisticated technologies, the team made direct measurements of Whistler waves produced when a laboratory plasma becomes unstable and generates runaway electrons. By better understanding this process, they hope they can reverse engineer it and create Whistler-generating antennas to prevent electrons from getting too fast. Runaway electrons also occur in nature. They are energized when lightning strikes or solar substorms disrupt the plasma environment of the Earth's ionosphere, which is the atmosphere's ionized upper layer. Scientists have theorized that Whistler waves regulate space weather, and may help mitigate the damaging effects of energetic electrons on satellites orbiting the Earth. We have known that runaway electrons drive Whistler waves in the ionosphere, during natural events, which led to theories that runaways would also drive similar electromagnetic waves in the tokamak plasma, said ORNL's Don Spong, who led the study. Observing Whistler waves helps us better understand their underlying physical mechanisms, which could open an avenue to develop new techniques to control runaway electrons and keep them from potentially damaging fusion reactors. As we learn more about the characteristics and excitation of Whistler waves in tokamaks, we may be able to mimic similar behavior to protect plasma-facing components. The team's experiments took place at the DEAD National Fusion Facility, a DOE user facility, which is operated by General Atomics in San Diego, California. The full findings were published in the journal Physical Review Letters.